How many of you have seen reactive streams before? Well, it's quite a few of you. I hope I still have something new to learn for you. How much of you know a lot about the HTTP protocol? A fair amount as well. We'll see. Let's start with some introductions. Oh, excuse me. This is me. I'm Berwout of Robles, which is quite a difficult name to pronounce in any other language than my own. I work at the Professional Development Center of InfoSupport. We help with project startup, mainly. We give developers the tools they need to do their project. And as such, I help them set up their continuous integration pipelines and stuff like that. So a lot of Jenkins, usually. That's not what we're here for today, though. Today, we're here for a list of topics, actually. We're going to start with a bit of a history on the HTTP protocol, like why we needed HTTP2, and what are the features that help us achieve that need. Then how do we use HTTP2 in practice? How can you use it in your applications? Then we're going to go over reactive streams. And I'm going to start with a small demo. And then there's a larger demo where you're going to have some audience participation. You're going to need your cell phone. And after that, we're going to take a short look into the future, which is not too far away, because in June, HTTP3 is coming out. And we're going to have a little look at what that brings for us. So a short history of HTTP. It started with HTTP 0.9, invented by Tim Berners-Lee in 1990 and 1991, which was before I was born. It was a one-line protocol, which meant it was very simple. It was designed for HTML documents only, and it was request-response. So you would send a request to the server, and you would receive a response back, and that was it. It looked sort of like this. So you had a GET request, which requested a resource. And then you'd receive a response. You had no headers or any complicated stuff yet, because it was only meant for HTML documents. Then some other people jumped on the train and formed HTTP 1.0. It was formed between 1991 and 1997. And actually, it became very popular very fast, because browsers emerged, and people started being able to view content online. And it had many differing implementations because it was so popular. There was no governing body yet. And in 1994, the HTTP working group was formed to address that issue, that everybody was implementing their own standards, basically. So in 1996, they actually made the first publication of HTTP 1.0, which said, this is how most people use it, and this is how you should probably use it. But it wasn't actually a set specification yet. That changed later, but first, this is sort of how it looked when you did a request back then, before we had browsers. It had some features of note, HTTP 1.0, compared to the previous version. Request and response headers. For the first time, we could say something about who was our user agent or some metadata. We had a response status, so we knew if the request failed or if it was unauthorized or something else happened. And for the first time in history, we had content types, which was very nice, because now we could send other things than just plain HTML, which basically the internet was born. We had an HTTP 1.0 request, and that looked a little bit different. We still had the verb, which meant what you wanted to do. We had the resource identifier we had earlier, and then from here on out, it goes a little bit different. We had a version for the first time, because they thought they might make new versions in the future. And we had a bunch of headers added, a blank line to separate the headers from the request body, and then any data you would want to send. The response, for the first time, we had a status line, so we could know what happened. This one succeeded, which is nice. We had some headers as well, then a blank line, and any data. All right, so on to HTTP 1.1. It's used from 1995 till current days. Actually, the last publication was in 2014, which is pretty recent. And the reason I say current here is that as of today, the web is only using the top 10 million websites on the web. Only 38% of them are using HTTP2 right now. So a lot of the web is still just HTTP 1.1. It was the first formal standard by the IETF. Basically said, everyone, you have to implement this. So it was set a bit more set in stone than HTTP 1.0 was. And there were publications in a number of years. It had a few nice features as well. It had keep alive by default. They realized that if you send a request and receive a response and then terminate your connection, you spend a lot of time opening TCP connections and doing a lot of handshaking. You could reuse the same HTTP connection if you just kept it alive, so you can reuse it for new requests. And they made it default, so you don't have to give a header, and it always keeps alive, which also meant that the HTTP 1.0 requests you were sending were now also being kept alive, which was kind of nice. We had chunked encoding, which allowed us to send large files over a data stream. So you would start a request, and you would receive a response, but it would be chunked. So you would receive a bit of a response, and then a bit more, and then a bit more, and then when the server was done, it would end with just a blank line. And this allowed us to basically, in TCP, we already split the data up into chunks, and then we reassembled it and sent it up to the application layer, where you have your image, basically. But what this allowed us to do was, instead of waiting for the full image to get to the transport layer on our side, we could give parts of the image to the application layer already. So if you've ever seen a picture load on the web and load line by line, that's chunked encoding being used. And it's a much nicer experience than sitting at a page and having nothing happen, and then all of a sudden your image pops in like 35 seconds after. We had cookies, which was our first way to store state about the user, to do logins, all that sort of stuff. We're kind of annoyed by them now because of all the laws surrounding cookies, but it was a nice feature. OK, so we have all these nice features. What is the actual problem we were facing? Why did we need HTTP2? We had a couple problems. We had an extreme growth in connected devices. Not only your desktop computers or your mainframes were connected anymore, but it's also your cell phones, your fridges, your ovens. Basically, everything was getting connected, and the processors were getting smaller and smaller. And for the smaller processors, the protocol was also kind of heavy. We had a problem with responsiveness. Google and Facebook started making websites more responsive, and basically users stopped coming to your website if it took 3 seconds to load. So we needed to be responsive, and we needed to be able to deal with high volumes. And also, we had nothing for the server to send you any data without you requesting for it. So it was always request response. There were a few solutions in the past for the responsiveness problem. We had polling, which how many of you still use polling today? It's basically you ask a server, hi, can you send me an update? It sends you an update, and then you ask it again every 5 seconds. And it seems very responsive for your user because you do it in the background, but it's actually not very nice for the server because it's a lot of load that is unnecessary because it may not have an update. Then we had long polling, which was a little bit nicer. It's basically you tell the server, hi, whenever you have an update ready for me, just send it to me, and then you wait. But there was a big drawback of long polling, which was that it kept your HTTP request open. And that meant there were resources being held, and you could only open a limited number of those connections. So if you did a lot of long polling, you could get blocked, basically. Then there were WebSockets, which were very nice, actually, but they basically took over the protocol. So you did an upgrade request to upgrade to a WebSocket, and then you're basically saying, well, we're no longer talking the HTTP protocol. We're just going to talk binary for now, and you could send both ways. But it was a nice solution to the bidirectional problem. The only problem it had, everybody started inventing their own protocols because they still wanted like a structure to do it in. But nowadays, there are so many libraries out there that WebSockets are still pretty good. And we had server-sent events. And server-sent events were actually, they were a cheat of the chunked encoding we had. We used them to send large files, but they figured out that why not send small chunks of data with chunked encoding. So we would send a request to a server, hi, I would like to receive data. And then the server would just send you small updates every time, and then a line when it's finished. So it was our first way of of doing sort of a bidirectional thing, where you could subscribe to a topic. It had the same drawback that long polling did, which was that it kept your request alive for a very long time. All right, so HTTP 2.0 was supposed to be a solution for all of this, or it was made to be the solution for all of this. It started developing around 2012 when Google started a protocol called Speedy. They made it binary for the first time. So where your HTTP 1.1 requests, if you were snooping on the line, you could basically read whatever the requests were, as we saw in the earlier slides. Now it's just binary data. Since HTTP 2.0 came out, browsers have basically said you can only use HTTP 2.0 with SSL, which is nice because it guarantees like a form of protection. The protocol itself does support plain text, but your browser doesn't. So that's kind of neat. The HTTP2 working group basically took the specification by Google, the Speedy specification, had it reviewed by Facebook and some other companies, and then they made it into the HTTP2 specification. And then now the features of note, which is what we'll see, were made to address the problems that we saw earlier. So we have a bidirectional feature. For the first time, a server can send us sort of unrequested data. I'm going to come back to that a little bit later. It's called server push. We have header compression. We figured out that with HTTP 1.1, because it was a text protocol still and you could read the full request, you're always required to send the full set of headers. But if you send headers back and forth, usually in my session, like my user agent isn't going to change. It's going to stay the same the whole time. So it's kind of a waste to keep sending the same data back and forth. So they realized that they could compress those headers quite a bit and make it faster to work with. So there was server push and multiplexing. And this was the big one for me at least. It allowed your HTTP requests to go over the same TCP connection. So now instead of opening a new TCP connection for each HTTP request you did, you open one connection and all your data streams go over this connection and they're multiplexed just like in TCP. All right, that sounds pretty cool. How do we use HTTP2? This is actually the best feature, I think. It's implemented in your web servers and browsers. So as long as you update your web server to a fairly recent one and you've updated your browser in the last year, I would say, you're already using it. So you don't even need to change it. It's supported by all major web browsers and all major web servers. If it's not supported by yours, I wouldn't call it a major web server. Back to server push for a second. Server push is pushing from your web server to your browser cache. And it's basically saying that if you request this file, you might also want these files in the future. And the browser can either accept or deny them, basically. But when the user asks for them, they're already in the browser cache, which is the nice thing. They're defined using a link header. So you would add a link header in your HTML file, and you'd basically say, I want this to be preloaded. And then your browser will decide whether or not it wants to preload from that resource. The advantage it gives us is this. So previously, we would have to request the HTML, and then we would realize, oh, but we also need this styling, and we also need this JavaScript. So we're going to open new requests to get those. But now you can request the HTML, and then the browser responds with, oh, here's the HTML, but you might also probably need these files. And it just gives them to your browser cache, and then when you ask for them, they're already on your side. The multiplexing part meant that server-sent events got a new life, like a new leash on life, because the big problem with them was that they held up your connection. But now you can have as many server-sent event streams over a single TCP connection because it's all multiplexed. So the whole problem sort of disappeared, almost disappeared, actually. I'm going to get to that in the end. There was a big problem with head-of-line blocking, which is where a couple of long requests would hold up your whole application. And that's now solved because of multiplexing. So it's very nice. These server-sent events tie into reactive streams a little bit. And we're going to start talking about what reactive streams are, basically. So if you start reading about reactive streams, these are some of the keywords you might recognize. But if you look at these keywords, they don't really mean a lot to me. And when I started reading about them, I was like, well, this all sounds very cool, but I have no idea what this is. So I figured I'd look up what the main goal was. And the main goal is to govern the exchange of streamed data across an asynchronous boundary, which also did not tell me a whole lot. So I figured I need some sort of real-life metaphor for this concept of asynchronous stream data. And I figured, what can I use? And I landed on an orchestra. And I'm going to lay these terms we just saw side by side with the orchestra just to see how they fit, basically. OK, so composable is pretty obvious in an orchestra, right? So we can basically take different flows of music and compose them together. We have some sort of flow control. We have the director that can wave a stick, or the musicians can decide to go faster or slower based on the notes they're reading. We have message-driven, well, music-driven in this case. It's kind of a concession, but it's close enough. It's resilient. If an orchestra member has a bloody nose or stops playing, you're barely going to notice, at least if there's more than one of them, basically. It's responsive. When the director waves the stick to make something happen, the orchestra members all have to respond really fast, like within 100 milliseconds, or otherwise you're going to notice. It's elastic, which means they can play hard or soft. It doesn't matter. They can stop playing partially, like only one person can be playing, and it still sounds nice like music. They can play very furiously, or they can play very sturdy, and it doesn't matter. It still sounds like music. So it has this elastic property where it widens or it narrows. It's asynchronous. When the director waves his stick, not all of the audience or not all of the orchestra players respond in the same time. They have to decide for themselves when they want to respond to the triggers. So it's asynchronous. And this one was a little bit hard. It's back pressure. It basically means you're sending too much right now. Can you please slow it down a little bit? But in an orchestra, I guess it would be either a player playing way too fast and the director waving him back or something, or maybe the audience leaving or something. A little bit simplified. There are publishers, which are the musicians. There are subscribers, the audience. There are asynchronous streams in the middle, which is the music you're hearing. And reactive streams is a collection of interfaces that helps you deal with all of that. And what that means is that it's sort of like the director combined with the sheets of music that they're playing. Then there's this nice analogy I found where back pressure is made as a volume button, which is I thought that was pretty cool. But in a diagram, well, it seems pretty simple, right? So let's see how that works. I'm going to show you with Spring 5 and Reactor, but there are a bunch of libraries out there that can do this sort of stuff right now. For Reactor, there's a few specifics you need to know. There's something called a flux, which is a publisher that emits 0 or infinite events, 0 to infinite, sorry. So it's just a music player, basically. There's a mono, which emits 0 or 1 event, which is also like a music player, but maybe the weird guy in the back with like the gong or something that does ding, and you don't hear him for the rest of the show. There's a processor which is both. It's an in-between block. You basically use it to attach your upstream publisher to a downstream one, so it can publish, but it can also subscribe. And there's a subscriber, which is a subscriber. All right, let's see that in action. So I figured the orchestra was a nice metaphor, but then I thought, can I also build an orchestra? So I figured, how would you go about that? And I opened up my my IntelliJ. Let me see. All right, is that visible in the back as well? So you have your basic Spring Boot REST controller. How many of you are working with Spring and have seen this before? That's good. You have a get mapping which returns a publisher, which is a flux in this case, as you can see. I'm making a flux with a factory method called just, and you can give it a list of elements, and it gives you a flux. And then I'm delaying the elements by a duration of 1 second. And if you see over here, the media type it produces is a text event stream value, which is the server sent events I was talking about earlier. And then to receive these events, I made a very basic JavaScript file, which has the functionality of a new event source, which connects to my flux. And then when the event source receives a message, it publishes it, and on an error, it closes the event source. And published basically just means I'm going to add it to the inner text of the document. So when I run this, it gives us, with a delay of 1 second, each element from my flux, which is kind of, it's our server sent events, basically. So I figured I would need to send music to people to be able to make an orchestra. So we're going to make it a little bit harder. Here's my second flux. It still returns our text event stream value, but it's now going to send us notes, and it's going to send us with varying duration, with varying delays, because music has a tempo, basically. And then I'm going to use this concat operator, which is one of the composability features. It lets you add fluxes together in a certain way. This one just puts them behind each other. So when I try and run this, we're expecting to see our music notes up here, which they did not. There we go. I needed to get a new JavaScript. All right, so we see the differing delays. Like the next 4 will go faster, probably. All right, so now I just send this to everyone, and then we can make music, right? Not quite, because what happens if I open another screen? It starts from the beginning. So if I wanted to make music, distributed music, I would have to get all of you to go to the page at the same time, which I think might be pretty hard. This is one of the differences we have between a cold flux and a hot flux, whereas a cold flux is one you subscribe to, and it sends you all the events from the history as well. And a hot flux you subscribe to, and it sends you events that are currently happening, but no past events. So we need to switch to a sort of hot flux, which gets slightly more complicated, but it's still fairly easy. We now have a stream service, which is just a way to hold all my subscribers, basically. Then we have our third flux right here. Still returns a publisher, but we now need this in-between block, the unicast processor, which means it casts to one flux, basically. We put the processor in a list. It's our subscriber as well as a publisher. And then we publish it. And we have the clients auto-connect to it. And what this does is it allows me to, if we look at the stream service, it allows me to broadcast for each of my processors. I can call the onNext message, which basically fires a new event into their flux. So how you would see this is basically, it looks very much like the observer pattern. You would subscribe to something, and then when something new comes in, you call the onNext function, and it gets handled by the unicast processor and put on the flux. And the add is just, well, we just add it to a list of processors. And then I have a way to publish into those, which is just an endpoint for me to publish a value. And all it does is broadcast it to all our subscribed clients. All right. So when we run this, we get nothing because we haven't published anything. Now let's see if we can publish something. Let's publish E5. See, it lands in our stream. But now when we connect one of our new clients, it doesn't get the history from the previous versions, but it does receive all the new notes at the same time as the rest of the clients. So now we can make music. So I figured I'd go a little bit further than that, and I actually try to make music. So we have a real demo for that. I do need your phones for that. And also, there's a very specific set of instructions. I have you divided into sections, like a real orchestra. So the front row is section A. The left over here, let's see, basically this section, section B. Over here, section C. And over here, section D. And it doesn't really matter if you're in the wrong one, but it's going to sound cooler if you're in the right one. All right. So you have to turn on your mobile cell phone sound, hopefully only your media sound, because otherwise you might get called. The best is to switch your phone to 4G internet, because it's the most synchronous, I would say. You navigate to my website, and then you enter a username, which is just your name followed by the sections I just gave. So front row section A, B, C, D. The room name is JSpring, and the name cannot contain any sort of numbers or figures or whatever. It's just letters. And then you hit join. And then it could already play some sound depending on what phone you have. No, without minus sign. Sorry, it's just JSpring, all one word. So I see a few of you are in here already. That's me. Let me turn my sound off. It's best to turn your sound all the way off, because it's not super loud. So you can see how this feels kind of reactive. Like I push a button and everybody responds in their own time, but sort of at the same time. So it's also very responsive. I can also play with the volume a little bit because how hard I press the key matters. Like this should be pretty soft. And then that should be pretty loud. I can play around with the sections, as in I have these buttons on my keyboard here. And if I turn off one of the buttons, one of the sections gets disabled. So I can play with only the front row. If someone's cheating, you can hear now. I can check whoever's phone's working best, I guess. So I can actually make a reasonably decent orchestra out of an audience that's never played before. So I thought that was cool. And it shows you that the reactive streams actually function really nice. We used to already have, you could do this with just WebSockets, I guess. But the advantage of reactive streams over WebSockets is that you're basically you're working with the HTTP2 protocol, so it's no longer a binary protocol where you can do whatever, but you have this nice structure which all your web servers understand and they know how to optimize for it. All your firewalls understand it and they know how to optimize for it. It doesn't use weird ports or anything like that. It's just on your HTTP protocol, which is nice. There are a few difficulties with reactive streams, though, that I encountered, and I wanted to share them. Naming is relatively hard, and I found it more so in Spring Web Flux, because they're called fluxes and monos and unicast processors, and those are things that don't directly have like an image for me. So it's very hard if you connect like 3 of those in a very specific way, and you add a filter, and then you end up with a result. And what are you gonna call that flux? Like, yeah, it's this thing that emits a value every 3.5 seconds that's divided by 2, and it's sorted alphabetically or something. And then what is it named? So naming is kind of hard. Error handling on disconnects is fairly hard, because if you disconnect your phone from my application by leaving the browser page, your phone doesn't send me a signal. And actually, I tried doing that, like on close, send a post request, I'm leaving, basically. But your browser is like, well, my user is trying to leave, so I shouldn't finish sending that request. So it never arrives. Sometimes it arrives, half of the time, basically. So you have to do something to figure out if your users are still there, if your downstream connected subscribers are still there. And you can do that with a heartbeat or something. You would send them a request every 500 milliseconds or every second, and then when it errors out, you know something is up, basically. So I used, for the room, I actually used a heartbeat to monitor if you're still in there. And if you leave, you also leave, and it's done with the same reactive streams. Yes?
What is the problem? Like you want to send something, client is left, then you can handle the error and
Yeah, you can. Yeah, but if you wanted to use it for a view like I did, then the user wouldn't be gone until I send him something new. And it could yeah, and it could be that that doesn't happen for 20 seconds or something. So if you want it to be real-time updated, you need to check if your subscribers are still there. But in some cases, that is not a problem at all. Composability quickly becomes complexity. It's the same thing with the naming problem. If you have a bunch of reactive streams and you add them together in a specific way, it gets kind of complex fairly fast. So you should be careful where you want to use it. You should only use it for use cases that you really need it, I would argue. Then a little bit of the pros and cons versus WebSockets. There's a large amount of support right now for WebSockets still. A bunch of developers know how it works. There's a bunch of protocols you can use. It's built into a bunch of frameworks. So it's not bad to still use WebSockets. WebSockets are fine. If the client is sending a lot of individual requests, it's probably better to do WebSockets because you still have the overhead of having to send headers. And yes, they're compressed in HTTP2, but it's still larger than just sending binary data over the line. So if you have a large amount of bidirectional data to the server, but also back, and you need something that is very real-time, something like this, probably WebSockets are still a good option. There are many use cases where you don't need that, and it's nicer to have firewalls or web servers that understand your traffic, though. Then a little bit onto the future. What does HTTP3 bring? And to go into that, we need to remember this multiplexing picture we had earlier. All this data is getting sent over a single TCP connection. And in TCP, if one of your packets goes missing, what it does is it halves your throughput for a slight second before it starts back up. So if one of the stream's consumers is being slow, then my whole connection gets halved, and all my streams are impacted, which is not very nice, because all the other streams might be functioning correctly. So what they... like with HTTP2, actually Google started a protocol to make this work. They started QUIC in 2013 already, which was basically HTTP2 over UDP. So they took the UDP protocol, which doesn't care about lost packets at all, and then they built the TCP protocol on top of that. So they added metadata to every packet to basically make it acknowledge the same way TCP would. And then they sent HTTP2 frames over that TCP connection. So it allowed you to open 6 TCP streams on a single UDP stream, which when a packet gets lost, it doesn't have your throughput. And you could just adjust the congestion for the single TCP stream that got lost. So now it's more, the congestion is less on the level of the TCP layer and more on the level of the application layer. You get more control over how your application functions, basically. So right now, they voted to make, actually back in October, they voted to make QUIC, which was HTTP2 over UDP connections, HTTP3. But they're going to continue a little bit with that. It's not only going to support HTTP2 in the future. The TCP over UDP design is going to be used for other protocols as well. But HTTP3 is the specific name now for the version that was basically QUIC over UDP. Then a little bit about my setup. I had basically my keyboard connected to my laptop, which sends MIDI signals. Those MIDI signals, I use a WebSocket to send them to my Azure server in the cloud. And then from the Azure server in the cloud, I use Reactive Streams to send them to your cell phones. And the nice thing about these streams is that Reactive Streams APIs also supports connecting to WebSockets. So you can just use a flux all the way down your application. And it was running on one of my favorite web servers, which is Traffic. Traffic makes it really easy to get your SSL certificates in order. You basically say, I want to have an SSL certificate, and it goes to Let's Encrypt and asks them for one. And you don't even have to do anything for it, basically. It's kind of nice. And it all runs on Docker on an Azure machine. That was my talk. Please don't forget to rate it in the application. If you want to check out the slides, they're over there. Feel free to email me if you have any questions or ask them right now. And thank you for listening. And I hope you have a great drinks session in a second. I hope we have one. Yeah.